Now let's prove this interesting theorem. An element is of order n of a group G if and only if it means this element, right? It generates a cyclic cyclic subgroup of order n of G. Okay, so it's important to distinguish these two orders. Okay, order n, order n. In the first occurrence here, this order n means the order of this element. Okay. On the other hand, this order in the second occurrence is the order of the subgroup. Okay, so they mean that their meanings are different. So be careful. Okay, let's prove this theorem. So this says if and only if. So we have to prove both directions. This only if and if. Okay, so let's prove only if part first. So let A be an element of G with of order n. So what this means, so A is of order n. This means so E is a to the power of 0 and a squared, a cubed, and so on up to an minus 1. So they are all distinct, and a to the power of n is equal to the identity element. Okay, so that's what this means. That's what being of order n means for an element. Okay, then let us define the subset H by the powers of a to the power of m, where m is any integer. Okay, then this is a cyclic subgroup of G. In case you forgot the definition of cyclic subgroup, it just means that all the elements of the subgroup is represented as a power of some element of G. Okay, in this case, every element of H is a power of A, so it is a cyclic group. And of course, you should show that this is a subgroup, but I think it's easy enough to show or see. Okay, so this is a cyclic subgroup of G. The next thing we need to show is that it is a subgroup of order n. So that means the number of elements of this H is actually n. So that's what we are going to show. So this is what we are going to show. Okay. So let's consider any element a to the power of m in H. Take arbitrary element m, a to the power of m. By the division algorithm, we can express this m is as qm plus r, where r is between 0 and n, and q and r are of course integers. Okay, so a to the power of m is expressed as a to the power of qn plus r, which we can split as a qn times a to the power of r. But this part, a to the power of n to the power of q times ar. But since a is of order n, so that means a to the power of n is equal to the identity element. But if you take the power of identity element, it's still identity element. So we have this. So after all the elements of H can be reduced to one of these elements. By this transformation. So therefore, the order of H is n. Next, we need to show the converse, so if part. So to show this, suppose, so its converse is, it generates a cyclic subgroup of order n. Okay, so suppose H is a cyclic subgroup. Of G. And it's a cyclic subgroup, so it must be generated by some element. So generated by A. Okay. And suppose the order of A is P. Say P. Okay, so that means E A squared up to a to the power of p minus 1, they are all distinct, and a to the power of p is equal to the identity element. But as we have seen in the previous part, such an element of order p generates a subgroup, a cyclic subgroup of order p, right? But A generates a cyclic subgroup of order p. P is the order of A. So this means p must be equal to n because H is supposed to be generated by this A. It's a cyclic subgroup generated by this. But A generates a cyclic group of order P, so this P must be equal to n. So we are done. Next, we see a related theorem that says a finite cyclic group, G has subgroups of all possible orders. So what does this mean? All possible orders. Okay, so to understand what this means, let's say H is a subgroup of G. Then by Lagrange theorem, we know that the order of H divides the order of G. right? So it must be this must this must hold. So all possible orders means that uh, the sub the orders of subgroups are the divisors of the order of G. So that's what this means. So let's say if the order of G is, let's say, 6, then the all possible orders of the subgroups of G must be 1, 2, 3, and 6. So these are all possible orders of subgroups. Okay, let's prove this. Suppose the order of G is n. Okay, and let's say n is a multiple of m, so m times d, and if there is any subgroup of G, then that the order of that subgroup, if the order of the subgroup is m, then it must divide n like this. Okay, and since G is assumed to be a cyclic group of order n, so all elements of G can be expressed as a power of some element a. Okay. Where k is 0, 1, 2, up to n minus 1. Okay, and let H be a subset of G generated by a to the power of d. Okay, where r is integer. Okay, so all elements of H are powers of a to the power of d. Okay, and of course a to the power of d belongs to G. Okay, now this d is this d. Okay, so a to the power of d to the power of m is a to the power of dm, which is a to the power of n, which is equal to e, because a is assumed to be the generator of G, and the order of a is n, so this must hold. And also e and a to the power of d and a to the power of 2d, so that is of course a to the power of d to the power of 2. Okay, and a to the power of 3d and a to the power of 4d and so on, a to the power of m by m minus 1d. So all these elements must be distinct. So they must be different from each other because the order of A is n. And all of these have, so the exponent of these elements are less than n. So they must be different. And, so that means a to the power of d to the power of 0, a to the power of d to the power of 1, a to the power of d to the power of 2, and so on, up to a to the power of m minus 1. So they are different. And if we add one more integer to the exponent, then this must be equal to e, right? So this is equal to e. Therefore, the order of this element, a to the power of d, must be equal to m. So that means H, the order of H, therefore the order of H is equal to M. So, we're assuming M is any divisor of N. So for all divisor of N, we can do this argument. So therefore, there exist all subgroups of all possible orders. And we are done.